Okay, exceptions to the octet rule. Of course, every rule needs exceptions, right? What if we have an odd number of electrons? These are called free radicals. And you may have heard of that. Having issues with doceri is reconnecting. So you sometimes hear about free radicals. Nutrition experts will say you need to make sure you get enough antioxidant vitamins to combat the free radicals. A free radical is just a molecule or an ion that has an odd number of electrons in the Lewis structure. Do you think a molecular ion with an odd number of electrons is going to be a happy molecular ion? No. It's probably going to be quite reactive. It's going to react with something else to get octets, right? It's got that lone electron, that odd electron, and it's going to react to get that paired up. So free radicals tend to be unstable and reactive. When you've got free radicals roaming around in your body, they can cause undesired reactions, and so antioxidant vitamins help to get rid of those free radicals. So let's draw the Lewis structure for one of my favorite molecules. No! Because all caps is yelling, right? Looking for green here. Okay, so no. Well, it's an N connected to an O, right? How many valence electrons? 5 plus 6. 11. Okay, that's an odd number. We're in trouble. What do? We just do the best we can do. So we've got 2 for the bond, 4, 6, 8, 10, 11. Okay? Nobody has an octet. We could probably make at least one of these atoms happy. With an odd number, there's no way we can make them both happy. We can't have octets for both. So let's take a lone pair from the oxygen, because it is closer to an octet, and make a double bond. So put that in there. Now this nitrogen has 2, 4, 6, 8. The oxygen has 2, 4, 6, 7. So we could also write this another way, where we give oxygen an octet and the nitrogen's got 7. Right? If we make a triple bond, we're going to end up with one of them having more than 8 electrons, and that's not going to be good. So the Lewis model can't handle everything. It can't handle free radicals with odd numbers of electrons. NO does exist, especially in air pollution. It's very reactive, and so it does bad stuff, but it does exist. So how do we choose between these two? Formal charges. Okay? We want to minimize formal charges. If there's a negative formal charge, we want it on the more electronegative element. So let's look at formal charges. For this first one, cutting the bond in half, wrong color, cutting the bond in half. Nitrogen brings in 5 electrons, leaves with 6, so it's got a -1 formal charge. Oxygen comes in with 6, leaves with 5, +1 formal charge. What about down here? Nitrogen bringing 5, leaving with 5. Oxygen bringing 6, leaving with 6. Which is the better Lewis structure? The bottom one. Because here we have 0 formal charges. So if you've got an odd number of electrons, you just do the best you can. Another exception is an incomplete octet, meaning fewer than 8 electrons. Some elements tend to form incomplete octets. The one we've seen already, which has its own rule, the duet rule, is hydrogen. But some of the other smaller elements will also have less than 8 electrons. Boron and beryllium are small elements that tend to do this. So boron forms compounds in which it has only 6 electrons. So an example of this is BF3. So that's your third best friend. BF3. Fluorine's more electronegative. It's going to be in the terminal positions. We've got 3 times 7, 21, plus 3, 24 electrons. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's our 24 electrons. The fluorines have octets, but boron doesn't. Boron's a little guy. He's sometimes happy with that. Well, why not do a double bond? If we do a double bond, we can give everybody an octet. So let's look at what happens there. Just take a lone pair from one of those fluorines and do a double bond. This one looks better because everybody's got an octet, right? But look at the formal charges. So fluorine likes to make how many bonds? 1. Because its Lewis symbol has 7 electrons, one of them's unpaired. So anytime we see fluorine with an octet and 1 bond, that's a 0 formal charge. So this one's 0, 0, 0. And boron here, how many valence electrons does boron have? 3. It brought 3 to the company here, and if we cut these bonds in half, it leaves with 3, 0 formal charge. If we do the double bond and satisfy the octet rule, these fluorines have 0 formal charges. This fluorine has a formal charge. Brought in 7, it leaves with 6. It has a formal charge of +1. What's the formal charge on the boron? -1. This is better. Lower formal charges. And here we have the negative formal charge on the less electronegative element, so that's also bad. So this is not a good one. Now this will tend to react in such a way that it completes the octet on the boron. But this is a very valid Lewis structure. So boron and beryllium will often have incomplete octets. And you decide to give them an incomplete octet when it gives you better formal charges. Any questions? So the opposite of not enough is too many. So an expanded octet. This only works for larger elements. Elements in period 3. So our friends that we've been dealing with, carbon, nitrogen, oxygen, fluorine, are all in period 2. They cannot expand their octets. In period 3, the valence electrons are in the 3p sublevel. There is a 3d sublevel that is empty but available. For elements in the second period, there's 2s and 2p. There's no 2d. You'd have to go up to 3s, and that doesn't happen. So group elements in period 3 and above can expand their octets by pushing electrons into the d orbitals. And we can get up to 12 or even 14 electrons. So let's look at AsF5. So arsenic. Arsenic's going to be in the middle, and we've got 5 fluorines. And we can tell already that the octet rule is going to get violated, right? Because we've got 5 bonds there. This arsenic has 10 electrons. Yeah?
Why would you put the last fluorine on arsenic and not another fluorine?
That's an excellent question. why not do this? Why not just make a little string out here, right? If you do that, you'll find that you're going to have formal charges. So arsenic has 5 valence electrons. Fluorine has 7. So we have 5 plus 5 times 7. I believe that's 40, right? So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Kind of looks like a weird flower. Do those fluorines have 0 formal charges? Yeah, you can count the electrons and do the subtracting and stuff. Or you can say, well, fluorine likes to form 1 bond. It's got its 7 and the 1 bond. It's good. Arsenic is in what group in the periodic table? Group 5, which is the same group as nitrogen, right? But if we look at formal charges, arsenic brought in 5 electrons, and it's leaving with how many? 5. 0 formal charge. So if we, since you asked, let's do this. We're going to move this guy. Now I've got a problem. I lost a pair of electrons here. Where should I put them? Well, fluorine can't expand its octet because it's in period 2. So the only place I could put them is on the arsenic. You can count those. So now I've got this fluorine, and these over here are going to have 0 formal charges. I can just tell that because they have 1 bond. Here we've got fluorine with 2 bonds. That's going to be a non-zero formal charge. Right? So it brought 7 and it's leaving with 6. So the formal charge on that one is going to be +1. And arsenic brought 5 and leaves with 6, and so that's going to be -1. So that's not as good. Lewis theory is actually a very simplistic theory, and it's amazing that it works so well. So that's not so good. That make sense? And I would encourage you to try different things. You can be creative with Lewis structures as long as you follow the rules. And there are sometimes kind of crazy things, but then when you look at the formal charges, it should always point to a very limited number of results. So SF6, sulfur, and the fluorines. So there's 4 fluorines. We got to get 6 more in there. Sulfur's in period 3. It can expand its octet. So by putting those fluorines on the sulfur, they still have a single bond, and so that's probably going to be good because they'll have 0 formal charge. How many valence electrons does sulfur have? 6. So forgetting about the lone pairs on the fluorines, if we have 6 bonds around the sulfur, it brought 6 electrons, it takes 6 electrons, it's going to have a 0 formal charge. So that's going to work. So then we'd have to fill this out with all the dots. When you draw these Lewis structures on paper, make sure that your dots are large enough to see, okay? So that's sulfur hexafluoride. Any questions? Let's look at sulfuric acid, H2SO4. So for oxyanions, We've got, SO42 minus, NO3 minus, etc. The oxygens are going to be around the other element. And that fits with put the more electronegative ones on the outside. So sulfur is going to be in the middle and put 4 oxygens around it. The hydrogens go on the oxygens. So for all of these oxyacids, the hydrogens go on the oxygens. So I'm just going to pick those two. So we've got 2 hydrogens, and then we've got the sulfur, and we've got 4 oxygens, and so I believe 32. Please tell me if I'm wrong. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Well, that looks nice, huh? Is that an expanded octet on the sulfur? No, it's got an octet. Does sulfur do regular octets? Yeah, sometimes it does. Formal charges. Which of these elements has 0 formal charge? Hydrogen always. And this oxygen, right, has an octet and 2 bonds. This one has an octet and 2 bonds. So we can just kind of ignore those. They're going to be 0. This oxygen has an octet but only 1 bond. It's going to have a formal charge. So if I break this bond in half, it's leaving with 7 electrons. It brought 6 in, and so that's a -1 formal charge. This one down here is in the same boat. That's also a -1 formal charge. What's the formal charge on the sulfur? It brings 6 electrons, leaves with 4, so +2. So here's sulfuric acid without an expanded octet. Let's do it with an expanded octet. Oops, that's not what I meant. What did I do? Okay, that's better. So sulfur, oxygen, hydrogen, oxygen, hydrogen, oxygen, oxygen. Now, if I'm going to expand the octet, that means I'm going to have more than 8 electrons for the sulfur, right? How could I do that? Double bond. Which of those oxygens would really like to have a double bond with sulfur? This one and that one, because then they'd have 2 bonds, which is what they would like, right? So let's try that. I got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Now that violates the octet rule, but sulfur's in period 3. It can do that. This oxygen now has 0 formal charge, right? Has an octet with 2 bonds. You can do the math. This one has a 0 formal charge. What's the formal charge on the sulfur? 0. Is that better? Yeah, it's better. Okay? Yeah.
You talk about atoms or elements in period 3. What about lower periods?
Anything period 3 or larger.
Period 3.
So period 4, 5, 6, 7, those can all do expanded. This period 1 and period 2 cannot, ever. It's not large enough. Any other questions? Yeah.
Are we ever going to have to worry about transition?
We're not going to draw Lewis structures for transition elements because those are metals. And with very few exceptions, we're just drawing Lewis structures for covalent molecular compounds. Yes?
So in the second structure, they all have a zero formal charge?
Yeah. Yep. Any other questions? I wanted that to be the end. Oh, it's not. Just one more slide. We're going to do it. Let me finish it. Okay. Write the Lewis structure for XeF4. Or what do you think is going to be in the middle? Xe. And because fluorine's the most electronegative, so fluorine's got to be around the outside. I have to count up electrons. So xenon has 8. And 4 fluorines, they each have 7. So that's 28, and 8 is 36. So we got 2, 4, 6, 8. 10, 12, 14, 16, 18, 20, 22, 24, 26. Whoops. That was ugly. 26, 28, 30, 32. I have 4 more electrons. This is the opposite problem of not enough, making multiple bonds. Where do I put them? Give them to the big guy. Xenon is period 3 or larger. It's actually period 5. It can expand its octet. And so I'm going to give lone pairs to the xenon. I can't give them to fluorine because fluorine can't do an expanded octet. So I really don't have any choices. If I string fluorines, if I move this fluorine over here, it's just going to make everything worse. And so we're not going to do that. And so there we are. If you do formal charges, you'll find out that they're all 0. Write the Lewis structure for H3PO4. So PO4 is a lot like SO4. The phosphorus is in the middle, and the oxygens are around it. When this is made into an acid, the hydrogens go on the oxygens. You can try it other ways, but it's not going to work out very well. So there's 3 hydrogens. So valence electrons, I've got 3 times 1, 5 for the phosphorus, and 4 from the oxygens. Let's see, 24 and 8, 32. Yeah. 2, 4, 6, 8, 10, 12, 14. 16, 18, 20, 22, 24, 26, 28, 30, 32. That looks nice, doesn't it? Do all of those atoms have 0 formal charges? No, this oxygen doesn't. We can tell that without doing math because oxygen with 0 formal charge usually has 2 bonds like these guys. So these guys are all cool, but that one isn't. And phosphorus brings in 5 valence electron, leaves with 4, it has a +1. So what can we do? Phosphorus can expand its octet. Double bond. So we can take a lone pair from that oxygen and make it a bonding pair with the phosphorus. That gives phosphorus more than 8 electrons, but that's okay. Phosphorus is big enough to handle it. That gives this oxygen a 0 formal charge and the phosphorus a 0 formal charge. Any questions? That's enough to make you dangerous.